Welcome back to After Hours Engineering. We've made it to our last component, the sequencer. I've saved the worst, the best, for last. It is by far the largest of all the components, comprising nearly 50% of the code base. The only other code comparable in size is the top module. Because sequencers are large and complex components, I've decided to split this episode into 3 smaller episodes. Let's take a look. In episode 7a, we'll look at sequencer and their 2 typical types, the microcode and the control matrix. Then we'll look at state machines and more specifically the mealy. And finally, we'll look at a manual way to actually control the signals that go out to any particular kind of device. And that will be represented in a test bench. In episode 7b, we'll take it to the next step and build a very simple finite state machine sequencer. And then we'll build a test bench to drive that sequencer. In the last half, we'll build a partial synthesis environment. We're not interested in actually deploying to the hardware, but we are interested in investigating inferred latches. And in episode 7c, things begin to change. We'll start off with an overview of the final control matrix that drives the A09. This is where we will get a very brief glimpse of the A09 Softcore. It's a very complex control matrix, but it's easy to understand once we see the diagrams. So what is a sequencer? In its simplest form, it is a finite state machine, or an FSM, that acts as a data flow manager or a data interpreter. Its job is to control the flow of information. Here we have a diagram, and in the center is a sequencer that emits a bunch of control signals. Let's imagine that we want to move data along this path to various locations. Perhaps we'll start with the memory, so we'll adjust these control signals to route that data here. We'll use a few more control signals to select the right input and route it here, and yet another couple of signals to route it through here and to the program counter, and probably a few signals to load the program counter. Now the question is what is this sequencer? What is it made of? How is it implemented? Well, there are many ways to manage the flow of data in a processor, and the 2 most common variants are a microcode sequencer. For example, Ben Eater's CPU uses this type of a sequencer, in that there is a counter which provides an address to a non-volatile memory, and on the output, on the data lines, it generates the control signals. The other type of control sequencer is a control matrix, and more often than not, the core of it is implemented as a finite state machine. And in our processor, our FSM is going to be a mealy FSM. And in that case, we have both a synchronous section and a combinatorial section. I've sprinkled a little bit of Verilog here to give you an idea of how the symbols line up with the Verilog. You can see here in our always statement, we are looking at the positive edge of the clock for this section of the module, versus this section of the module is looking at the state variables that are stored within the memory itself. Because they can grow quite complex, even for small processors, we're going to start things off by reducing the complexity down to a manual process. We'll use a test bench to act as the FSM. Okay, but what is our goal? Let's take a look. Here we have a diagram of the test bench we will build. It's a visual representation. In our test bench, we'll have 4 components, 2 muxes, a program counter, and a register that we will call the memory address register. Our goal is to move this constant value through this flow down here and through the mux and get it loaded into the memory address register to here. That's our goal. So let's take a look at the test bench, the manual version of the test bench that will drive this workflow. Here we are in our manual test bench. In the upper right is the diagram that we'll be referencing. We have various local parameters set up, the clock, the manual signals that we're going to toggle and control, the output of the address register, the wires that are connecting in between the components. Those are the dashed purple lines. And now we have the 4 components that are in the diagram. We have the PC counter mux, the program counter itself, the PC. We have the mux that interfaces with the address register, and then the address register itself. Here's our clock that we do our work with and synchronize on, and this is the beginning of the test bench. Again, as a reminder, on the positive edge we do setups, and on the negative edge we take action. So here we're resetting both the program counter and the memory address register, and we wait for that to take action. Then we disable those, and now we're setting up our select statement, or our selector if you will, on the MUX PC. We're also enabling the loading of the PC so that the data that's routed through that MUX goes into the PC itself. Again, we take action. Then we disable the load. We update the address selector on the address MUX. We set the load or enable loading of the address register. We take action, and then finally we disable the load and wait for that to happen. And then we add a couple extra cycles so that we can spread the signals out in the GTK Wave viewer. That is the test bench. Now let's take a look at the GTK Wave output. In order to see the output in GTK Wave, I'll need to run the simulation. I already have that set up, so here it goes. And there is our simulation. We're going to compare the output of our test bench with the GTK Wave output. So let's take a look. We'll start from top to bottom. You can see here that on the first positive edge we're selecting the reset and memory address to be low. So if we come over here into GTK Wave, sure enough, those 2 signals went low. We also expect on the next positive edge for them to be set high. And sure enough, on the positive edge, we see them being set high. On the next positive edge, we expect to see the source selector set to 10 and the load on our program counter to go low, or enable loading on the PC. Let's come down here to the program load, and sure enough, it's gone low, and the source selector went to 0, 1, 0. That's what we expected. Great. On the next positive clock, which will come over here, that's this one right here, we are going to disable the load on the PC, set our selector on the address MUX, and then activate the loading of the memory address register. Now before we do that, let's take a look at the program counter. Here is the output of the program counter. Now this looks strange. This is the wire from the output of the program counter to the input of the MUX address. And sure enough, its output went to FF. That's that value, that constant value that we just loaded into the program counter. So yay, that's ready to go. On the next positive cycle, we bring the memory address register low. And on the negative edge of the clock, we expect the address register to get loaded. And sure enough, we have successfully completed the task. Our manual operation moved the data from the MUX through the program counter and finally into the address register. It's all working as we expect. And we did this manually using the test bench as a control, as our finite state machine. Okay, we've successfully emulated a sequencer by manually manipulating the control signals ourselves, just like a puppeteer. In the next episode, we transition to an actual FSM that will control the same 4 components, moving the same reset vector into the memory address register. So until next time,